Yoni Kahn visiting us from UIUC. So Yoni graduated from MIT actually 1 year before me. After that, he went on to do postdoc positions at both Princeton and Chicago before getting a faculty position at UIUC. So Yoni's worked on a lot of topics in beyond the standard model physics, in particular dark matter, and he's very well known for the abracadabra axion experiments. And so today he's going to tell us some of his more recent ideas for dark matter experiments, in particular relating to condensed matter systems. So take it away.
Thanks. So thanks so much for the introduction. And as I was telling some people at lunch, I'm a theorist, but I like to live like epsilon close to the theory experiment divide. So this talk will sort of be some superposition of theoretical stuff and also some experimental results from my colleagues who are actually trying to help build some of these experiments that I've helped develop the ideas for. So questions during the talk are encouraged. Yeah. So I don't think I need to convince anyone in this room that dark matter exists. I think the era of showing rotation curves first has probably been surpassed by just the amazing data that we have from the CMB. So temperature anisotropy in the CMB, you Fourier transform, you get these amazing set of peaks. You can fit the whole universe with 10 numbers, but to 4 decimal places, something must be gravitating that doesn't feel the pressure of photons, so it doesn't have an order 1 electric charge. So that's dark matter, at least from a cosmological perspective. It is nonetheless true that all of the evidence we have for dark matter thus far is purely gravitational. So some of the open questions about dark matter are, what is its mass? Does it have any non-gravitational interactions? And how was it made in the early universe? This is not an exhaustive list of questions, but if you answer some of these questions by postulating some answers using some viable benchmark models, so writing down some Lagrangian that lets you trace the history of dark matter from the very early universe all the way through today, then you can ask the question, how can you detect galactic dark matter on Earth? Ideally using some of its non-gravitational interactions, which can be stronger than gravity. So I know that some people here are interested in looking for purely gravitationally coupled dark matter. I think that's extremely important because we don't know if the answer to question number 2 is yes or no. However, as I'll hope to convince you, there is a lot of open parameter space where the answer to question 2, does it interact non-gravitationally, is yes. And we can really learn a lot by doing some very small scale experiments to probe that parameter space. But to do so, you can't just be a high energy physicist. In fact, the fact that dark matter sits in high energy physics is kind of hilarious because this is the canonical low energy experiment. Dark matter is non-relativistic. All you ever need is quantum mechanics, at least to describe what it's doing today. And so the tools that one needs to use are tools borrowed from other fields of physical sciences, condensed matter physics, chemistry, material science, quantum information. If you really want to know how dark matter is interacting in a detector on Earth, you need to be comfortable conversant, if not fluent, in the languages of all of these fields. And so I found it very interesting and enjoyable to start to learn some of these techniques. And I think it's a really nice way to help dissolve some of these interdisciplinary boundaries to help us all kind of, aim at the same science goals, no matter what our backgrounds are. And I think the people here are a great illustration of this. So, talking to people today in Dave Moore's group, people coming from AMO that are now doing fundamental physics. I think we just need more of that. Okay, so just a brief review of what dark matter is doing near us. So here's a nice n-body simulation picture of a Milky Way-like galaxy. The reddish blob and all those bright spots are not light, but just density of dark matter. So our galaxy is mostly dark matter. It extends way out past the visible light radius. So if you look at an edge-on view of a Milky Way-like galaxy, you see the spiral arms that bulge, and then there we are about 8 kiloparsecs away from the center of the galaxy. So just by doing gravitational measurements, you can learn a couple important numbers. You can use the virial theorem to equate the average kinetic energy to the average gravitational potential energy of a test particle. Because gravitational and inertial mass are equal by the equivalence principle, the mass cancels out. And so instead what we learned roughly is at a radius r of 8 kiloparsecs, how fast is dark matter moving? And the answer is on the order of thousandth of the speed of light, about 300 kilometers a second, which is also of the same order as how fast our solar system is moving around the center of the galaxy, also within a factor of a few of the gravitational escape velocity of our galaxy. By looking, for example, at motions of stars in and out of the plane of the disk, we can learn about the local dark matter density in the vicinity of Earth, and it's about 1/3 of a proton's worth per cubic centimeter. But again, that doesn't tell us what the mass is. It just tells us the product of the mass and the number density. So dark matter can be made of a few heavy particles or lots of light particles. And so part of postulating the answer to what dark matter is involves choosing a mass which then fixes the number density. And that informs what kind of experiments you would want to do in order to look for that kind of dark matter. Okay, so here is the landscape so far of dark matter with mass above about a GeV. There are an amazing number of experiments. Actually, a lot of them are basically just off the top of this plot. When I was in graduate school, this plot kind of only extended to up here. And just the fact that it has just continued to go down, 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 down is amazing. We are basically seeing zero background events of multiple tons of stuff buried deep underground or in a mine shaft or under a mountain. So this kind of blue down here is when you start to confuse dark matter events for neutrinos. There are always going to be neutrinos around. You can start to disentangle these, but your kind of return on investment becomes increasingly worse as you go deeper down. And that's basically what this darker shading is meant to represent. The shapes of all these curves are similar. As you go to higher masses, mass goes up, number density goes down. So flux goes down, and you just see fewer and fewer dark matter particles. And so that's why these lines go up and to the right. And then you hit a brick wall at low mass, because whatever your detector is doing, you have some energy threshold, a minimum energy below which your dark matter wouldn't do anything detectable. And so all these detectors have different energy thresholds, but that's what kind of sets the vertical scale here. Fortunately or unfortunately, all of these results have been null so far. We have not yet made a discovery in this parameter space. There's an obvious way to keep marching down, just build a bigger and bigger detector and wait for longer. But I'm going to be interested in what happens when you go off to the left. There really is an unexplored frontier for dark matter lighter than the proton, exploiting this fact that given the mass density, your number density goes up as your mass goes down. So that means that a smaller detector, roughly speaking, would give the same event rate. You can make a discovery with 10 grams of stuff rather than 10 tons of stuff. And just from a purely practical perspective, that means that your return on science per dollar is really unbeatable in this parameter space. This is just an example of a plot from one of these snowmass white papers on the landscape of sub-GeV dark matter. So on the y-axis is the scattering cross-section with electrons, x-axis is the mass. This is some model where you postulate one of those benchmarks. So in this case, the thing mediating dark matter and standard model interactions is some very light particle, kind of like a photon. So in that case, there's a well-defined way to produce the right amount of dark matter that gives you this orange target for the right cross-section that would get you the observed dark matter density. And the goal is to do experiments that cover this target everywhere. As you can see, we're getting there, but we're not there yet. So this parameter space is not really infinite. It's pretty bounded until you can come up with another model that gives you a similar theory curve here. So before we say that we have no idea what dark matter is, we really need to do experiments to cover this entire orange region, and then we can kind of decide what the next best thing to do is. So if you want to look for dark matter lighter than the proton, a question you have to ask yourself is, does your detector behave like a bag of free particles? And as particle physicists, every calculation you do in quantum field theory starts by assuming you start in the vacuum state of the universe. So you're just there playing, relativistic pool with your beams at the LHC. However, in condensed matter physics, your vacuum state is like this ball pit. This is like the ground state of a system of interacting electrons. There's all kinds of stuff doing all kinds of complicated things, some crazy entanglement with the wave function of your ground state. Now the question is, what happens if you drop a child into this ball pit? Everything kind of moves around. Some things move more than others. There's lots of collective effects. You might start to see some waves. And this is really the context in which you need to think about dark matter scattering. So to be a little more quantitative, we know the velocity of dark matter. That means if I tell you what its mass is, I can tell you the relevant momentum and energy scales that are suppressed by factors of v and v squared, respectively. Your detector is a bag of free particles if these E and P are the largest scales in the system. This is a separation of scales, which should hopefully be familiar to those of you that think about EFTs. So the reason that, for example, the LZ experiment can treat the xenon nuclei as if they were a bag of free nuclei is that if your dark matter is much heavier than a GeV, its kinetic energy and its momentum are much, much larger than things like the atomic binding energy. However, as your dark matter mass starts to drop below these scales, you start running into relevant many body scales in your system. The energy it takes to liberate an electron, the energy it takes to excite a semiconductor from the valence band, or an electron in a semiconductor from the valence band to the conduction band. The energy it takes to excite an out-of-phase oscillation of nuclei in a lattice known as an optical phonon. And then for axion-like dark matter much lighter than EV, the dark matter itself has macroscopic coherence, behaves like a wave, and kind of pushes on your system all at the same time. So this is meant to illustrate for you that thinking about condensed matter physics is actually mandatory, not optional if you want to look for sub-GeV dark matter. You cannot just treat your detector as a bag of free electrons. So I'm going to give you two examples of experiments that are looking for dark matter using some interesting condensed matter systems. So the first will be looking for scattering of sub-GeV dark matter on these anisotropic organic scintillators. Those are words that I wasn't super familiar with maybe 5 years ago, so I'm not assuming anybody here has thought about chemistry in a while, so I promise I'll lead you through these things gently. So let's start just by asking what happens in a generic detector, symbolized here by this cartoon of a rubber ducky. So your dark matter comes in non-relativistically with momentum m chi v, and it leaves having deposited some energy and momentum into the system. So it is a reasonable approximation to treat the dark matter as if it were a free particle, because if dark matter were interacting strongly, we would have seen it already. So it's fine to think of these things as plane waves. And so then there's an energy momentum relation. So given a momentum transfer q, the dark matter must have lost energy omega sub q to the target. Working this out just gives you this expression q dot b minus q squared over 2m pi. However, if your target is not made of free particles, the constituents of the target are not necessarily momentum eigenstates. So there's no need necessarily that this momentum q had to go into some plane wave state of momentum q in your target. In general, the question you want to ask is, if you poke this thing with momentum q and energy omega, does that click with some energy eigenstate of the target? This is just a sort of a generic setup for this where I'm not committing to any particular form of the Hamiltonian for the system. And so the correct object of study is what's known as the dynamic structure factor. It's an example of a response function. A response function just says you poke a system with some perturbation, what does it do? You calculate it is you weight by all of the energy eigenstates of the system omega f, the inner product of this plane wave state with your initial state and your final state. And here this is summing over all of the constituents of the system. Here Rj might represent all of the position operators for all the electrons in your system, or all the nuclei of your system, depending on what you imagine the dark matter is interacting with. And then the interaction rate is an integral over some things that depend on the dark matter properties, like the dark matter velocity distribution and the so-called form factor that tells you whether dark matter is interacting through a light or a heavy mediator. But then the thing that you're integrating against is this response function S of q and omega that only depends on your material properties. So this is a general framework for scattering. You can also do this for absorption that works for any many-body system, and it's a convenient way to sort of parameterize what kinds of functions are going to be good for interacting with the dark matter that has the kinematics that we know of in our galaxy. Okay. A nice thing is that this formalism tells you under what circumstances you expect a daily modulation of your event rate. This is a very, very powerful signature. So the Earth rotates at a frequency with respect to some fixed stars that's a little bit less than 24 hours. It's a sidereal day. That's a very distinctive period that tells you your signal is coming from outer space and not on Earth. There are very few backgrounds you can imagine that modulate at exactly that same frequency. If you see an oscillation on a daily basis of your event rate, that is as close as you're ever going to get to a smoking gun for dark matter. So how might that happen? So your dark matter velocity distribution in the frame of the Earth is actually time dependent because the Earth is rotating. So you're just going to do some time dependent rotation of the dark matter velocity distribution as seen from the galactic frame. If your dynamic structure factor is peaked at particular directions of the momentum, then this integral can also depend on time. So basically, because Q and V are tied together by the requirement of depositing energy omega Q, if the distribution of V depends on time, your response function depends on the direction of Q, this oscillating factor will make your rate change, even if the mean dark matter speed doesn't appreciably change over a day. I'm not talking about using like the equatorial velocity of the Earth to give yourself a boost. This is not the same thing as daily modulation. This is a very distinctive effect. And what's really neat is that it is easier to see this effect for light dark matter than it is for heavy dark matter. And I'll explain to you why as we get to the details of the experiment. So basically the goal is find some material with an anisotropic dynamic structure factor or response function, and that will let you see some daily modulation in the rate. So I just want to point out that I'm not saying that you need to know the direction of some outgoing excitation. So your target is not necessarily made of momentum eigenstates. It is not necessarily true that if I hit it with momentum q, something is going to go in that direction of q in the target, and then I have to track it. Instead, what I'm saying is that this function represents the probability of something happening. And that probability can be anisotropic. And so therefore your rate can inherit the anisotropy, even if whatever you detect is not necessarily going in any particular direction. The directionality is coming from the incoming dark matter correlating with the probability of exciting something in your detector. Okay, so let's take another look at the kinematics. So the rate for a fixed velocity is just the integral over this dynamic structure factor. And that thing lives inside a parabola bounded by this equation. So for example, if your dark matter had mass of 100 MeV and a velocity of 10 to the minus 3 units of the speed of light, your momentum transfers are on the order of hundreds of keV or below, and your energy transfers can be up to the kinetic energy of the dark matter, which is about 10 eV. This is an interesting range because it's sort of too high energy and high momentum for traditional condensed matter physics, but it's too low energy and low momentum for material science, studying things like radiation damage from the passage of alpha particles through a material. So actually, even for materials that we know and love like silicon, the properties of this response function in this regime are actually not super well explored. So you can kind of think about where the boundaries of this come from. So the upper boundary of this parabola is forward scattering, where the momentum transfer is parallel to the direction of the dark matter. At the apex of this parabola, you've stopped the dark matter, you've gotten all of its kinetic energy. And then over here, a lot of momentum transfer for very little energy transfer is like hitting a brick wall. So your goal basically is to find a response function that is large in this region so that when you integrate over it, your rate is large. So it turns out that atomic and molecular systems sort of coincidentally and naturally have about the right scales for sub-GeV dark matter. So this is the same plot as I showed before, but now a typical momentum scale is the inverse of the Bohr radius, which is alpha ME in natural units, so about 3 keV. And then a typical energy scale is the binding energy of hydrogen, alpha squared ME, which is 13.6 MeV, or 13.6 EV, or lower than that. As you pack more and more atoms together, they tend to form bonds that have lower and lower energies. So you get down from here to, for example, the energy gap in molecular systems or the gap in semiconductors, or even lower if you have kind of exotic systems like superconductors, they can have a gap that is very much less than an EV. But the point is, if you kind of look at the intersection of these scales, you can imagine coming up with a system where the response function is kind of peaked right here that sits inside your dark matter parabola. And then the only question is, depending on the mass of your dark matter, that depends on how far out you can push this right edge. So dark matter of mass 1 MeV only carries kinetic energy of order an EV. And so if your system has a minimum excitation energy of an EV, that tells you what the minimum mass of dark matter is that you can look for. Okay, so maybe before going on to details of the particular experiment that I'll talk about next, let me pause for questions here. Okay. So I got started thinking about condensed matter by thinking about graphene detectors. So a crazy idea that I worked on in my first postdoc is what happens if you had a detector made of a whole array of 1 atom thick sheets of graphene. So graphene is just carbon in this hexagonal lattice. And what we showed is that if you apply an electric field between this kind of array of graphene sheets, then an electron that's ejected from the graphene due to a dark matter scattering event will drift according to some velocity, and the direction that it is excited, the direction that it actually exits the sheet is directly correlated with the dark matter incident direction. So this is a directional detector, but I would say getting a kilogram of graphene is probably about as hard as getting a kilogram of microspheres. It is a scaling problem that is borderline impossible. However, the way electrons behave in graphene is very similar to the way the electrons behave in benzene, which is a much more commonplace material that you just buy vats of. The reason is that these alternating single and double bonds are characteristic of the way that carbon likes to bond in organic compounds. So there are some wave functions that stick out of the plane of here in the graphene sheet. And in the case of benzene, where basically you close off these bonds by attaching hydrogen atoms at each vertex of this hexagon. The wave functions responsible for electronic transitions are the ones where electrons live in these 2pz orbitals. The fact that they are out of the plane of the molecule makes the system anisotropic. There's a difference between out of the plane and into the plane of the molecule. So you get the order 1 anisotropy both for graphene, but also for dark matter scattering in benzene. The probability of exciting an electronic transition in benzene, we showed, is anisotropic. Benzene is also great because it scintillates. So once you've excited your electron, you're not liberating it from the molecule, you're exciting it to some molecular state. It de-excites and emits a photon of energy roughly equal to that excitation cap. And in benzene, it's like 5.6 eV. So your signal is a photon coming out of your molecule. You hit an electron and what you get out is light. So we actually were able to set a limit on dark matter electron scattering and do the theory calculation in the very same paper, which as far as I know is like the only case of sort of that being done. But it wasn't a fantastic limit, partly because we were limited by the dark rate of just kind of an off-the-shelf PMT, but also because it's a liquid. So the molecules are randomly oriented, so you don't get any of that anisotropy back. And then my colleague, Carlos Blanco, who this is another one of these like fortuitous coincidences, had an undergrad background in chemistry, pointed out that there are organic molecules that like to form crystals. And in that case, those things do have all the anisotropy that you want. One example is this molecule called transstilbene. So it still has this planar structure, which is characteristic of these carbon-carbon bonds. So we calculated its response function. I'll show you this in a little bit. But to prove that it has a good scintillation yield, this is a video of Juan Collar shining a pen light on this, a UV pen light on this thing. And it just lights up like a Christmas tree. So this molecule emits at about 400 nanometers, which is like 3.1 eV. That's a nice wavelength to try to detect these photons. The transition energy is 4.2 eV, so you lose a little bit of energy to vibrations and stuff. But that's actually a good thing because you don't want the emission and absorption spectra to lie on top of one another. Otherwise, you never get your photons out. So what's nice about the way that this material arranges itself in a crystal is that interesting and complicated chemistry displaces the emission and absorption peaks from one another, such that once you have a de-excitation, your photon makes it out with almost unit probability. So this movie is showing you, roughly speaking, the three-dimensional analogs of those inverted parabolas over the course of a day. There's like 4 of these beams because actually there's 4 molecules in a unit cell of this crystal. But what you can see is that depending on your dark matter mass, over the course of a day, these kinematically allowed regions traverse the peaks and troughs of the structure factor, which leads to about a 20% daily modulation in the rate over a very wide range of masses. So this is great. And so just the thing to take away from this slide is that here, dark matter electron scattering in the system gives you a daily modulating UV photon flux. So over the past 2-ish years, I've been trying to cajole, beg, borrow, steal my experimentalist colleagues' time to try to set up some sort of prototype demonstration this thing could work. And I think we're actually pretty close. So I want to show you some exciting recent results. It turns out that there's already been a lot of development on UV photon detection for astrophysics applications. One thing you might want to do is measure the light coming from various telescopes at a wide variety of wavelengths. And so these CCDs have started to be developed for UV photon sensing, which basically means you need to ablate away the back layer of the CCD in order to get the UV photon in. This has already been sort of prototyped at Fermilab. So along with Dan Baxter, who's been leading this, along with Alex Strelica-Wagner, we were able to borrow some of these CCDs and do an experiment involving some shards of stilbene crystal grown by the grad student of one of my chemistry colleagues at MIT. So basically what they did is they said, let's excite this crystal with a 295 nanometer UV LED. We're going to do kind of an on-off experiment where on is just expose the CCD to just this UV LED. Or sorry, off is exposed to just this UV LED. And on is pack these shards of crystal inside this optically clear epoxy puck, stick it inside this thing, and see if the lamp is going to excite scintillation in here that will increase the rate of detected photons. The answer is yes, this works. So on the left is a picture of what the CCD exposure looks like with the LED on, but no stilbene crystal inside it. So you still get some photons. These light and dark spots are like the number of electrons per pixel. You still get some rate, but they're actually, there's one of these fortunate accidents that these crystals had some sort of impurities that were kind of smudged that meant that this did not like to absorb this short wavelength UV light. And so actually no electrons were excited in these kind of dark spots. Then you keep the lamp on, but you stick the Stilbene puck inside it. And all of a sudden, your median rate of electrons goes from 4 electrons per pixel to 88 electrons per pixel. So something is very obviously lighting up here. And what's really neat is that these splotches are gone. Because actually, this CCD still likes to absorb light at the emission wavelength of the Stilbene, even though it didn't see any of the light from the lamp. And so if you look, so this is the number of pixels with 0 electrons. What you want to focus on is the number of pixels of at least 1 electron. So the blank with no crystal is down here. The crystal LED, you increase the number of such pixels by at least a factor of 2. So this is at least a proof of principle that this CCD can serve as a UV photon detector for electronic transitions that are excited in these molecules. So the next thing you'd like to know is it true that when you hit this crystal with dark matter, the rate at which you generate photons is anisotropic? So unfortunately, we can't make ourselves a beam of dark matter, but the closest you can get to the kinematics is using electrons scattering off of this crystal. So the kinematics are actually pretty closely matched. The electron has mass of, half an MeV, which is pretty close to the sub-GeV dark matter. You can't quite get the velocity right because actually very, very slow electrons not only basically do not penetrate the crystal, but it's very, very hard to get a clean enough vacuum. And then that becomes a kind of a hilarious consideration because the vapor pressure of these crystals is actually very, very high. So if you try to go to low vacuum to get your low energy electrons through, the crystal just evaporates. This is a thing that we didn't realize until Dane, who's the grad student at MIT leading this, did this experiment at LBL. But he managed to get a couple samples of crystals in there that had lower vapor pressures and get them in there for long enough to actually measure things. So what they did is they fired an electron gun at these crystals, masked different faces of them to try to correlate basically where the mask was with the axis of the crystal. And very, very preliminary results on a related molecule called parylene show that depending on where this mask was put, you actually do get a different flux of photons. So this is not dispositive yet because, one thing you might rightly ask is like, well, how do you know you correctly normalize this thing to the area of the crystal? So this is like fresh off the press, like data taken like 2 weeks ago. However, the rough count rate matches roughly what you would estimate by trying to calculate these response functions from like atomic orbital theory. So this is like a nice proof of principle that we think we know what's going on. The reason these things decay is that basically you are burning through the crystal with the enormous flux of electrons. So the more electrons you fire at this thing, the more the molecules basically get damaged and no longer scintillate. So you kind of have a limited range of time that you can see anything, on the order of milliseconds before the crystal sort of becomes non-scintillating. So there's some very interesting kind of combination of chemistry and material science and physics that go into actually doing this measurement. But this seems like the right direction to go in order to build a functioning detector like this. So the eventual goal is to do as follows. Why stop with one molecule? Every molecule that is in this kind of class of organic scintillators will have a slightly different excitation gap, a slightly different anisotropy, and probably slightly different background rates. So let's just make an ice cube tray of all of them. Put 2 of one molecule in here, 2 of some molecule in here, and then stick a CCD on top of it to capture, basically order, 2 pi solid angle of the photons that come out kind of going in the up direction. If you can do a little bit of light focusing, you do even better, because these so-called skipper CCDs have just an absolutely ridiculously low background rate per pixel. If you could focus most of your light on a single CCD pixel, your dark rate would effectively be negligible. The really neat thing is that the total rate of these Stilbene crystals, kilogram for kilogram, is about the same rate as scattering in silicon. So there's an existing idea to use 10 kilograms of these micron-thick silicon CCDs as both the target and the detector for dark matter scattering. And what we're trying to argue is that actually, if you can make this thing work, you can decouple target from detector. You can still exploit the same CCD technology, but it's a lot easier to synthesize 10 kilograms of organic crystals you can basically do in a fume hood, as opposed to all the fab it would take this to fabricate 10 kilograms of these CCDs. And you don't lose anything in the rate, and you get the benefit of 20% daily modulation, which will help if there are any backgrounds that we don't know about that will eventually sort of hit a floor. And indeed, right now, the Senti experiment basically sees no background in their 3 electron bin. there's this background at very low energies, which I think I first talked about when I saw you in Aspen pre-pandemic. That was the last conference that I went to. That despite our best efforts has not gone away. I think I'm no longer, I no longer think that could be dark matter. However, a background rate will eventually limit the sensitivity of any experiment like this. And the best way to get rid of a background rate is to look for a daily modulating signal that will allow you to subtract that away. So basically, these curves are showing you that, if you assume a background rate that's on the order of a count per minute or a count per day, eventually you can get to the same sensitivity, even in the presence of what would nominally be quite a large background, using this modulation as a statistical handle. So what's neat is if we can make this work, this is both an exclusion and a discovery experiment, kind of all packaged into one. Okay. Any questions on this? Because I'm going to move on to something completely different. Yeah.
Maybe. So this is a modulate. You're talking about this really nice directional sensitivity. You see a modulation with some shape and most of its power at a frequency of 1 over a day. Mm-hmm. But you're not actually measuring the momentum direction, like the direction in the sky. So I mean, this like very powerful daily modulation relies on it pointing to a specific place in the lab, because aren't there a ton of things that modulate throughout the day at that frequency?
So sure, but then I think the point is if you take data for a year, the phase difference between a sidereal day and an Earth day will eventually displace that.
Okay, so you rely on long enough that you actually see some.
Sure, because really, if you get down to these cross sections, you're talking about a few events per day. So you really need, for discovery significance, you need a kind of a large exposure. Okay. But the other game you can play is you can imagine rotating this thing with the Earth. Of course, that would probably bring in some backgrounds, because whenever you actively do a rotation, then that might also, cause some background there. But I think the real advantage is that you can have as many targets as you want. There's, ordered dozens of these organic molecules, all of which have very, very similar properties. And the combined statistical power of all those things, all pointing to the exact, if all of those funny looking shapes all match exactly what you would think, you could possibly even measure the dark matter velocity distribution that way.
Okay. Okay, thanks.
Yeah. Yeah.
There's a scion band on plot here. Is that the freezing?
Yeah, that's kind of the theory target you'd like to go after. So like we're kind of already starting to see it, at masses on the order of like hundreds of MeV. But again, I think we should take these limits still a little bit with a grain of salt, because the kind of calibration that we've done with these electron beam experiments has actually not yet been done with silicon. There's been no direct measurement of the response function of silicon using a standard model probe that has the same kinematics as dark matter. So UV photon absorption won't do it for you, because that's vertical transitions. Basically, a photon has momentum equal to its energy. You really need to be doing a scattering experiment in order to really measure the response function. So all of these curves basically come from theory calculations of what the response is, whereas we're hoping we can actually get a direct measurement of the structure factor using a combination of these electron beam experiments and also X-ray spectroscopy. Yeah.
So, Sean, how do you know how much of these crystals you need? How did you calculate that?
Yeah, so I mean, you can calculate the expected event rate for kind of cross sections that correspond to these well-motivated models as a function of the size of the crystal. And basically what you see is that you need on the order of like kilogram year exposures. So, either you have a few grams and you wait a really long time, or you really try to scale up, which is why all these dark matter electron scattering experiments are really going after a kilogram of target. And I think it goes without saying that if you can get the backgrounds under control, a kilogram of these crystals is easier than a kilogram of these sort of very high purity silicon CCDs. So it seems like a promising way to kind of get to the scaling behavior that you would need if you can make the prototype work. Yeah.
I mentioned it and I missed it, but where do you plan to have this experiment, like on the ground or?
So the idea is there's an underground test stand called Nexus at Fermilab. It's basically in the tunnel of what used to be a neutrino experiment. That's about, I don't know, 10 meters underground, I think. Or maybe, I can't remember. However, Snow Lab in Canada is the lowest background lab in the world. And they have a cryogenic test stand that is sort of waiting for new experiments to go there. The slight irony about using a CCD for readout is you don't want it to be too cold or your electrons freeze out. So probably you just want to like borrow some space in one of their extra tunnels in Snow Lab. But I've been in contact with their science directors, and they're very interested in these kinds of ideas. assuming that one could demonstrate that indeed the only limitation is the backgrounds, right? You really want to prototype these detectors and show that you would actually gain by going deep underground, but like those facilities are very open to these kind of small scale experiments.
Would it be affected by muons at all?
So it turns out there is a daily modulation to the muon flux at the level of about 0.2%. So probably that won't matter, as long as your daily modulation is 1% or less.
Thanks.
Yeah.
Are you worried about the scintillator crystals degrading on a year time scale? It seems like that could mask the sort of yearly modulation that you were talking about.
That is a good question. I don't know anything about the long-term stability of these crystals, but presumably that is a thing one can easily measure by just, well, that's an excellent idea for an experiment. I guess you stick a crystal in some sort of, maybe you stick it in this like kind of shallow Fermilab site, or you do these electron beam measurements on it, you wait for a while and then you do it again. But I guess if you do the electron beam measurements, you burn out the crystal. So you probably want to make two that are pretty identical. You take one to a lab, you measure it, and then you assume the one that you left there for a year looks kind of the same. My guess is that these things are quite stable, as long as you're not at, pressures that cause these things to sublimate. But I'm not a chemist, so I don't know. Great. Okay, so let me move on to actually, so one more thing about using molecular systems to do dark matter scattering, and then I'll start talking about some superfluid helium stuff. So this idea of the Migdal effect goes back almost 100 years. And the idea is that you can get an electron excitation if your primary event was nuclear scattering. Because in a molecule or an atom or a semiconductor, your electrons and nuclei are always coupled. You never have a bag of free electrons. So if you whack a nucleus, quantum mechanics says that you can induce an electronic transition that's suppressed by things of order like the ratio of the electron mass to the nuclear mass. So this is an example of an effect that exists outside of the so-called Born-Oppenheimer approximation, where nuclei are infinitely heavy and slow and electrons are very light and fast. This is neat because suppose your dark matter didn't talk directly to electrons, you could nonetheless avoid the threshold from traditional nuclear recoil by looking at EV scale electronic transitions. And because this exists beyond the Born-Oppenheimer approximation, it's an effect that's usually too small for condensed matter people to care about, which means that us high energy people can sort of borrow from the literature and take it over. So we worked this out in a very, very toy example of a diatomic molecule like carbon monoxide. And you get the same kind of anisotropy because your matrix elements between two different nuclear vibrational states are also directional. So you basically get this factor of the dot product of the dark matter direction and the direction of the molecular axis, one of which shows up outside an exponential and one of which shows up inside an exponential. So which of these factors wins depends on how large this thing is. And it just so happens that this combination of things is order 1 for dark matter of mass of about 100 MeV. So once again, just by accident, you land on just the right scales for the problem. And you get enormous daily modulation in the rate of electronic transitions following a nuclear scattering event, with this really neat thing that basically the phase of this curve inverts when these two terms are of comparable size. That happens for masses around 100 or 200 MeV. So from the shape of the modulation curve, you might hope to actually measure the mass of the dark matter. Once again, pound for pound, you expect about the same rate as you do in silicon for this kind of transition. Of course, you're never going to make a detector out of solid carbon monoxide. We expect that the same qualitative features will hold for these organic crystals, though now this is really truly a many-body condensed matter material science calculation that we have not yet done, but we're working with some material science theorists to try to understand how to calculate this effect in systems with more than just 2 nuclei. Okay, so moving on to the second part. So now I'm going to talk about axion detection with superfluid helium-3. So I think given the number of you that have worked on axion experiments, I can be a little bit brief with this review. So now we're no longer talking about dark matter scattering, we're talking about dark matter that is macroscopically occupied in phase space and behaves like a wave. So the dark matter axion field today has an amplitude set by the dark matter density. These same scales that we talked about before are going to show up. So the mass determines the frequency of oscillation. And then there are corrections to this, spatial variations on the order of the de Broglie wavelength of the dark matter. So the velocity is order 10 to the minus 3. So if for dark matter of mass 10 to the minus 7 eV, its Compton wavelength is about 10 meters, but its spatial coherence length is enhanced by another factor of 1,000, so about 10 kilometers for these masses. And so you're going to use the fact that your spatial and temporal coherence is enhanced by factors of 1 over a small number in order to look for a very, very, very small signal. So what kind of things should you measure? You should think of this thing as just some sort of classical field pervading the universe that's going to push on your laboratory apparatus. It can push on it in different ways. In vacuum, it can affect a magnetic field and generate through a small oscillating magnetic field. This, of course, is the operating principle behind Haystack, ADMX, Abracadabra, DM radio, all these axion photon experiments. However, the non-relativistic Hamiltonian for the axion also contains a coupling to nuclear spins that looks for all intents and purposes like an effective magnetic field. It's not a real magnetic field, it's not generated by moving charges, but it couples to nuclear spins as if it were one. Then there's the kind of holy grail, the irreducible coupling if your axion solves the strong CP problem, where your oscillating axion field induces an oscillating neutron electric dipole moment. I'm going to focus on this term, which is known as the axion wind, basically because this factor of the gradient, taking the gradient of this field pulls down the factor of velocity. So the gradient of the axion field kind of points in the average direction of the dark matter velocity. So just looking at the parametrics, so I've divided it and multiplied by a factor of the gyromagnetic ratio because spins have that factor of gamma. So depending on what molecule or atom or nuclear spin you're coupling to, you put a different value of gamma there. It's roughly 1 over the mass of the atom. So here I'm just going to put this for helium-3. It oscillates to the frequency of the mass, and it points in the direction of the velocity. If you ask for an axion that solves the strong CP problem, the so-called QCD axion, what is the typical size of this effective field in units that you're used to in the laboratory? For a mass of about 10 to the minus 7 EV that sits right here, that's about 5 times 10 to the minus 23 Tesla. That is a very, 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 very small field. And just to, to give away the punchline, I'm not going to describe an experiment that can get all the way there because it's incredibly hard. However, there's a lot of white space in this parameter space. There are very few experiments that have probed anywhere below astrophysical bounds, and I think it's worth going after kind of all of this stuff, at least while this parameter space is open. So the coherence time for these masses will be of order 40 milliseconds, and we're going to try to exploit that in order to achieve some kind of resonance analogous to the E&M resonances that one uses for these cavity photon experiments. Okay, so the traditional way that one would detect this axion wind was laid out in an idea by the Casper collaboration about 10 years ago. And it's borrowing techniques from NMR, nuclear magnetic resonance. So once again, kind of borrowing techniques from our colleagues in chemistry. So you stick some external magnetic field in your sample, and then you look at the evolution of the nuclear spins under the influence of some axion-induced magnetic field that points in the transverse direction. And what happens basically is these spins are processing around your external field, but they kind of go in this corkscrew thing where their tip angle away from the vertical is growing linearly with time if your axion mass equals the so-called Larmor frequency, which is this gyromagnetic ratio times the value of your external field. So this is your resonance condition. And the traditional way of looking at this is looking for basically your null is 0 tip angle, and your signal is a very, very, very tiny tip angle, therefore a very tiny oscillating real magnetic field you can pick up with a pickup loop oriented in the transverse direction, where the width of this thing is set by the coherence time of spins in the sample, which can depend on all kinds of things like the inhomogeneity of your sample and impurities and things like that. So I'm now going to describe a very weird phenomenon in superfluid helium that's going to let us couple to this axion effective B field. This is known as the homogeneous precession domain. So let me just narrate for you what's happening in this plot. So take helium-3, cool it to below 1 millikelvin. At certain pressures, it'll be in what's known as the B phase. That has to do with something about the order parameter in which the Cooper pairs of helium-3 fermions pair up into bosons and make this thing a superfluid. Hit this thing with a transverse magnetic field. If you have a magnetic field in the z direction that is not constant in space, but instead grows, say, going from up to down, then each one of these nuclear spins will field a slightly different Larmor frequency. So they'll tip at slightly different angles, they'll start processing at slightly different speeds. This system kind of looks just like a big mess. The magic of this particular system is that the spins spontaneously organize themselves into 2 domains, one of which acts like there is no precession whatsoever. So these spins are just totally relaxed and just pointing along the z direction. And another one where the spins are all tipped at this magic angle of about 104 degrees, and they're all precessing together at a frequency determined by the local Larmor frequency of whatever the B field is at this domain boundary. Over some period of time, losses in the system will decrease the amount of spins in this precessing domain, and therefore the domain wall will drift upwards. But as the wall moves upwards, the precession frequency changes. And so the signal of the system is a slowly drifting precession frequency and a very kind of large macroscopic magnetic moment from all these precessing spins. Like this thing is like a cubic centimeter. So, order 1 fraction of the container is all precessing at an order 1 angle tipped from the vertical. But the frequency is very slowly drifting, actually drifting at a rate that's determined by your choice of the gradient of your external field. So thinking from the axion perspective, the hardest thing about doing an axion experiment that's trying to be resonant is tuning your B field to scan potential axion masses and stepping from one to the other, to the other, to the other. This system scans itself. So setting a range of frequencies by your gradient of the B field, the gradient of the B field is not a bug, it's actually a feature that tells you that at every one of these possible frequencies, you could be in resonance with an axion. So here's how that would work. So your axion wind is going to induce a very small variance in the position of that domain wall. That domain wall, you should not think of as something you can actually observe. It's kind of just a useful theoretical construct. The actual observable is the precession frequency, or more precisely, omega dot, the drift of the precession frequency over time. So we worked out the statistics of this thing. So basically the 2-point correlation function of the axion-induced domain wall shift, but some realizations from this covariance matrix are shown here. So kind of nothing happens for a while, and we've chosen the precession frequency to cross the axion mass at a time of about 5 seconds. And you see exactly this kind of linearly growing thing. It's the characteristic of a resonance, and these kind of like after wiggles that persist for some amount of time. Roughly speaking, the axion wind is as likely to push you up as it is to push you down. So the mean of this thing is 0, but the variance is of order this number, a fractional frequency drift about 1 part in 10 to the 13. So that sounds like a scarily small number, but everyone here is used to dealing with scarily small powers in axion experiments, so maybe you shouldn't be too terrified. But this actually is kind of the perfect system for an honest-to-goodness quantum readout for the following reason. All of the information about the axion is buried in the phase of the precessing magnetic moment, or the second derivative of that phase, which is the precession drift. You learn nothing about the axion from the amplitude of that signal. So what you want is some kind of readout which is as insensitive as possible to the amplitude, but as sensitive as possible to the frequency. That sounds a lot like squeezing. And that's kind of where my thoughts on this kind of sat for a while, until I met some people at a conference in Santa Barbara on quantum metrology that told me that the right thing to do here is this technique called optimal quantum control. So this is like, I taught myself the bare bones of what I needed to know about qubits in a matter of weeks, but I think there's a lot more to investigate here. So hopefully some of you will have some useful things to say. The setup is as follows. So suppose that I'm reading out my precessing magnetic moment with some flux-sensitive superconducting transmon qubit. The axion magnetic field will act on that qubit by a time-dependent modulation of the level splitting in the qubit. I can think of that thing as a Hamiltonian that depends on a parameter that I would like to estimate. I would like to estimate the frequency drift omega dot. It turns out in this series of papers from about 6 years ago, there's a theoretically optimal way to gain the maximum amount of information about a parameter you're trying to estimate for a given measurement time. And their toy example was precisely this one, except they were just looking for a magnetic field of a constant frequency rather than something with an omega dot. But the derivation is very similar. You don't care about the amplitude A. That just sets the overall scale of your noise. What you're trying to estimate is omega L. And then the rate at which you gain information about the system can exceed the kind of canonical standard quantum limit. A time-independent Hamiltonian, you can gain Fisher information about the system at a rate of t squared. But for a time-dependent Hamiltonian estimating the frequency, you gain information at a rate t to the 4th. Omega dot, you gain information at a rate t to the 6th. And that boils down to up to the coherence time of your qubit, your error on your omega dot goes like 1 over t cubed. Then there's a really, really nice idea about, well, if your signal that you're trying to measure has a coherence time that's vastly larger than your qubits, all you need to do is timestamp each of your qubit readouts with an atomic clock. and then correlate the measurements after the fact. And therefore, you only lose a little bit of the scaling by the coherence time of the qubit T2. So basically, for times larger than the qubit coherence time, you have to kind of reset the system and measure again. But as long as you have a good enough frequency standard, you go from t to the -3 to t to the -5 halves, which is actually not so much of a penalty. So the only thing you need to do this measurement is a bunch of qubits that don't actually have to be that good. You don't need long T2, you just need a really, really good atomic clock. So using that as our sort of benchmark measurement scheme, we were able to kind of project the sensitivity. So these different curves correspond to different parameters of the experiment. So different volumes of superfluid helium-3. It's a very unusual and expensive kind of substance. So getting more than 100 cc's, my colleagues tell me, is not really feasible. But with about a month of measurement time, you can expect to now get beyond these astrophysical limits. And what's nice is, like, in each of these blocks, you don't need to scan. This is like you set your V field to have a gradient that varies by an order of magnitude over your sample. And then you just set the system up again and again and again and again, let it relax, and just do this over and over and over with kind of no external tuning. And you get the scan over the resonance if the axion is anywhere in here each time you set up the experiment. The dashed and solid curves depend on kind of the parametrics of what you're using to do your optimal quantum readout. The dashed line is if you had a single qubit with 100 microseconds of coherence time, that's kind of existing technology. The solid line is 100 qubits that have a millisecond coherence time. But actually, the way that your sensitivity scales is identical with the number of qubits and the coherence time. So actually, you do just fine with a lot of really crappy qubits, as you would do with a few really, really good qubits. So this is why I'm excited about this experiment. I'm part of this SQMS Quantum Center, where one of the goals is to sort of investigate the sources of qubit decoherence. And we expect to have kind of a lot of just qubits lying around that have sort of been investigated and sort of discarded. And then one can then use these things to do readout on the superfluid helium to start to look for this axion wind. One other kind of annoying feature is that this particular phase of helium-3 destabilizes for B field larger than about half a Tesla. So you have a hard upper limit on the highest axion mass you can probe with this setup, but going down, you can kind of go down as far as you want. It just turns out that basically your sensitivity degrades a little bit as you go lower in frequency. So you kind of have to decide how much time you want to spend down in this stretch. Okay. So just to summarize, I think the future for light dark matter, by which I mean sub-GeV particle dark matter, but also axions, is very bright. This is a plot of the projected sensitivities for a lot of these experiments, looking for the axion nuclear spin coupling. This is another example for this no mass review of dark matter electron scattering. Kind of this key milestone is this benchmark model, and then there's lots of experiments that are expecting to get down here. We're uncovering new parameter space every day. But really, one needs to work with condensed matter physicists to understand the true sensitivity of the experiment. And I think this is the kind of thing I don't need to emphasize too much to this group, but support for small experiments really is crucial, because all of these are just ideas until you get somebody to go and do the thing and build the thing. The amount of time you need to take data to really get new parameter space here really does vary from like months to like a year or a few years. It is really doable on the timescale of a PhD. And so I'm really excited to see where this field goes over the next decade. Thanks.
Thanks for the great talk. So are there any more questions for Yoni?
Yeah, really beautiful stuff. So on this one where you're scanning the frequency of the gradient, does that imply the gradient, like the uniformity of the gradient, has to be good to impart into?
No, and that's the magic of this system. So basically, in any ordinary sample, if you had a gradient of a B field, your T2 star would just go to crap. This system does not have a T2 star, it only has a T1.
Okay.
So basically, there are spin supercurrents that rapidly redistribute the tip angle of the phase. There's condensed matter kind of serious condensed matter magic that goes into making this plot. But once you accept this is the kind of the coarse grained dynamics of the system, you don't need a precise B field gradient. Even if it went in one direction and turned back around, you just get basically two domain boundaries. Like, you'd like it to kind of be monotonic, but the uniformity doesn't matter. It's mapping out the B field that just tells you where the resonance is, but it doesn't change any of you don't need that to be precise at that level.
Okay. I'll ask you one.
Yeah.
So are qubits the right thing to use to read out this signal, or have you considered other kind of detectors?
So at first we thought about, okay, so what does it mean to measure a frequency? Well, like the dumbest thing you could do is just measure, the mx and my and take arctangent, but then you get amplitude noise. And so every other measurement technique we could imagine brought in amplitude noise, and you're never going to get your amplitude noise down to 1 part 10 to the 13. So the only idea that I could come up with that is only sensitive to the phase and not the amplitude is this kind of qubit react. I'd be curious to see if anybody has any other ideas, because this is, I'm not saying this is the only one, but it was at least a proof of principle that we knew worked, because actually what's neat is like both of these are experimental papers. Like they actually took data and showed that you obtain these scalings.
I'm thinking, for example, if you put it in an optical cavity and shine the laser to it, can you do anything interesting? But I have no knowledge of this.
So the problem is I don't think, I guess lasers coupled to B fields by like Faraday rotation or something, but I'm not sure if you get the required precision that way. Also, this whole thing has to be at like less than 1 millikelvin. So presumably a laser on it would heat the thing up. I don't know. But yeah, but these are the kinds of things that I'd definitely be curious to discuss.
Any more questions? Yeah.
Yeah, so can I like just way back and ask you like a very general question? So you were like throughout this talk we're talking about okay, where is the scintillators where you like are trying to probe the interaction between the dark matter particle and like organic stuff. So what like theory do we have an argument say, hey, here is like the supposedly the Feynman network of interaction between like a dark matter particle and normal stuff. And we were talking about say the sub-GeV dark matter and it can give you like much more size per dollar.
Yeah.
But I guess that's based on the assumption that like whether the mass of the dark matter like whatever that is, the interaction cross section is going to be the same, right? Like, do we have things that tells us this is right?
Yep. Yeah. So this is the part of the talk where if it was a more theoretical focused talk, I'd probably devote more time to this, but it's this Feynman diagram. So this is dark matter annihilation in the early universe that can set the relative abundance through what's called freeze out. You could turn this diagram around and turn the coupling down, and then you have a small amount of dark matter kind of leaking in from the thermal bath in a method that's called freeze in. Both those things tell you for a given dark matter mass, this is the cross section you expect for annihilation. Therefore, this is the cross section you expect for scattering, and that is what sets the orange line on this plot. It is not the only model, but as I mentioned at lunch, it is a viable model that you can trace back from temperatures milliseconds after the Big Bang all the way through today, passes all constraints, and so therefore we should go and look for it. So this tells you what is the dark matter electron coupling you expect for a given mass. Then you can go and figure out, given that interaction, how is it going to interact with the condensed matter system, and that's basically just exactly through the structure factor.
Any more questions for Yoni? Yeah, sorry.
You didn't talk about nuclear recoil other than Mantle effect.
That's right.
I'm just wondering what's the landscape of nuclear recoil?
Yeah, so again, as I mentioned at lunch, the landscape is sort of detector limited rather than sort of target limited. You need to build things like transition edge sensors that get you to like a milli EV resolution. I'm not the one who's building those things, and so that program is progressing. But it's hard because basically like the sensitivity scales inversely with the volume. So you want a tiny TES, but then you need a giant block of stuff to all get its athermal phonons to kind of land inside the TES. Whereas electronic excitations are, you can move an electron, you can apply a field, you can move it around. And then also from the theoretical point of view, it's kind of hard to come up with a model that only couples to protons but not to electrons that exist in this mass range. It's very hard for those things to pass all the constraints without a whole bunch of kind of jerry-rigging of the model building. So I would say in this mass range, I think the prior on things that couple to both nuclei and electrons is quite large. And so therefore, you might as well spend a lot of your time looking for the electron coupling. But that's a biased viewpoint. Yeah.
What about something like P minus L a couple of neutrons, I guess, like something with a P minus L gate goes on.
Right. Let's see. Sorry. If it's B minus L, then why doesn't it also couple to electrons?
Well, does it resolve? I mean, at these very small momentum transfers, I don't know. I'm asking.
No, but I think that's the point. It's like B minus L, like, you know, electrons carry lepton number, so it's gonna couple to electrons too.
Okay, yeah, you know
So-
better than I do. I'm
Right,
just-
no, so I think that, so, you know, it might not couple to protons, but that's like that's the contra, that's the opposite state, the opposite implication of what I was saying. I'm saying that it's hard to come up with a model that only couples to protons, that doesn't couple to electrons. Right? So your model is an example of one that couples to both neutrons and electrons, so then you might as well look for the electron part of the coupling too.
Yeah, maybe we could chat more after this. So we're talking right after this.
Yeah.
Okay. Right, so I think hopefully everyone's had their questions, so let's thank Yoni again. Yeah, Yoni will be around both this afternoon and tomorrow, so if you want to chat with him, you should register on this Google Doc. And if anyone wants to come for dinner, please email myself or Isaac. And I think we'll just leave from here around 5:45 for dinner at 6. So feel free to let us know if you want to join.